As we continue our journey through electronic components, we now turn our attention to the inductor. We will begin by describing the magnetic field a bar magnet creates, which will pave the way for us to grasp the concept of electromagnetism. Subsequently, we will be ready to understand inductance and our next component, the inductor, as well as its application in circuit design. An electric charge creates an electric field that is an imaginary area in which another electric charge experiences a force, the Coulomb force. There are positive and negative electric charges which can exist on their own. Now, on the other hand, there are magnets. If we look at a bar magnet, we can see that each magnet has a magnetic north and a magnetic south pole. Magnetic field lines travel from the magnetic north to the magnetic south pole. If we now wanted to have only a magnetic south pole, one would think that by cutting a bar magnet in half, we would get exactly that. However, it turns out that if we cut a bar magnet in half, we get two bar magnets with magnetic south and north poles. We can't create a single magnetic south or magnetic north pole. They always exist together. There are also ferromagnetic materials like iron, which can become magnetic. In iron, grain boundaries form during creation, with each grain acting like a tiny permanent magnet facing in a random direction. Due to this randomness, there is no net magnetic field. However, if we apply a large magnetic field to the ferromagnetic material, the grain's magnets align with the magnetic field. If the outside magnetic field is strong enough, the grain's magnets will be aligned even after we remove the external magnetic field. Now, the ferromagnetic material has become a magnet on its own. We can destroy its magnetic properties by heating the magnet, which randomizes the inner bar magnets again. There is a connection between electricity and magnetic fields, which is called electromagnetism. Electrically charged particles that move create a magnetic field. When there is a current flowing through a wire, a magnetic field is created, which forms concentric circles around the wire. We can determine the direction of such a field by using the right hand rule, which states that by gripping the wire and aligning the thumb in the direction of the conventional current flow, the other fingers will show the direction of the magnetic field. The magnetic flux density given in the unit Tesla gives us a rough idea of the strength of the magnetic field around the wire. The strength of the field decreases with increasing distance from the wire and increases with increased current flow. So, we have seen that current in a wire creates a concentric magnetic field around the wire. Conversely, a changing magnetic field can induce an electric current in a conductor. This process is known as electromagnetic induction. Let's assume we have a closed circular wire and a bar magnet. The magnetic field is constant when the magnet is stationary. However, if we move the magnet, the magnetic field the wire experiences changes. When moving the magnet away from the wire, the magnetic field decreases. Consequently, a current is induced in the wire. One of the fundamental properties of a magnetic field is that it wants to remain steady. If we suddenly turn off our power supply, the magnetic field won't immediately be gone, as it wants to resist the change. Instead, it will slowly decrease. The magnetic field change leads to an induced current and voltage. The induction keeps the current flowing and induces a voltage even though the supply is off. On the contrary, if we were to turn on the current again, the whole current wouldn't immediately occur because the magnetic field first needs to build up. In this case, an induced current and voltage in the opposite direction would be present before the magnetic field built up entirely. The wire stores energy in the form of magnetism. We characterize the ability of the wire or any conductor to store energy in the form of a magnetic field by a property called inductance, denoted as L and measured in Henry's H. Inductance is a measure of how effectively a conductor can store magnetic energy for a given current. It depends on factors such as the shape of the conductor, the number of the turns in a coil, and the presence of a magnetic core. We can calculate the induced voltage by multiplying the inductance with the change in current. V is equal to L times di over dt. We can increase the magnetic field of a conductor by creating many turns of wire to create a coil. The turned wire increases the inductive effect the magnetic field has, which forms the basis of our next component, the inductor. Often the inductor features a metal core which increases the inductance further. The symbol of an inductor in circuit diagrams is typically represented as a series of loops reflecting its physical structure and function. So, what are the use cases of the inductor that result from its properties? A capacitor wants to keep the voltage steady, while an inductor wants a persistent current flow. If we turn off a flowing current, the inductor would continue to push electrons in the direction of the flow for a while. If we were to turn on the current, the inductor would hinder the electrons at first before the magnetic field is established. So the inductor creates a lag in current changes, while a capacitor produces a lag in voltage changes. An inductor hinders instantaneous changes in current. And that's for what it's used. They are essential for maintaining steady current supplies, leveraging their energy storing capability in applications such as switching mode power supplies. Moreover, they are often combined with capacitors to form LC circuits, effectively reducing ripple in switch mode power supplies, where ripple is a periodic variation in direct voltage, typically stemming from deriving DC voltage from alternating current. When implementing conductors in a circuit design, they have a few implications. First of all, they are relatively spacious compared to capacitors. Further, the magnetic field they create can influence nearby signal lines or integrated circuits, which must be accounted for when designing the layout of a printed circuit board. Finally, inductors can be influenced by applying a magnetic field to them. Magnetic field lines are always present in a closed loop. Therefore, there can't be a single magnetic north or south pole. The interplay between electric charges and magnetic fields is called electromagnetism. Moving electric charges create a magnetic field. For example, current flowing in a wire creates a concentrical magnetic field around the wire. Further, if the magnetic field changes, current is induced in the wire. A magnetic field always wants to remain steady and stores energy. If we turn off the voltage source, the magnetic field also wants to maintain its current state and induces a current so it can continue to flow for a while. If we turn on the voltage source so current can flow through a wire, the magnetic field induces a current and voltage in the opposite direction until the magnetic field is built up. Consequently, an inductor creates a lag in the current. If we were to create multiple turns of wire, we could increase this effect and create something that is called an inductor. We measure inductance in Henry. Often inductors feature ferromagnetic metal core to increase the inductance even further. Ferromagnets are metals that become magnetic by applying a strong external magnetic field. We use inductors to store energy, to smooth a current supply, or in company with a capacitor to create a stable DC from a switch mode power supply. When creating the layout, we must carefully consider their placement so that their magnetic field does not influence signal lines or integrated circuits, and so it isn't influenced by a magnetic field itself. The full course is available on Udemy.